Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about structure engineering. Reaction influence line for statically determinate beams. Reaction influence line for statically determinate beams. Suppose we have to design a column-band column in the bridge. In order to correctly design the column, we first need to determine the maximum axial force that it will be carrying. This means we need to calculate maximum support reaction at point B. We say maximum because here the support reaction is not constant. It changes as the load moves across the bridge. We can determine the maximum force with rather ease by drawing an influence line. An influence line is a diagram. It shows how specific force in the structure changes due to it moving load. Here is the influence line for reaction at B. Before we come to know how we have drawn the diagram, let us know how to interpret it. The diagram shows the values for reaction at B, as it load moves across the bridge. For example, when the unit load is at point A, the reaction force at B is 0. When the unit load reaches point B, the reaction force becomes 1. When the load is over the hinge at point C, the reaction force at B equals to 2. The reaction force becomes 0 when the unit load reaches point D. When the unit load is placed at point E, the reaction force becomes 4. Negative sign means the reaction is acting downwards. Finally, the reaction at B becomes 0 again, when the unit load reaches point F. According to the diagram, the absolute maximum reaction at point B occurs when the load is at E. Since the influence line is drawn for a unit moving load, we must multiply the values given by the diagram by the actual magnitude of the load in order to obtain the correct reaction values. For example, if the moving vehicle exerts a force of 5 kN on the bridge, then the maximum negative reaction force at point B equals to 4 times 5, which is equal to 20 kN. And the maximum positive reaction at B equals to 2 times 5, which is equal to 10 kN. So, column B goes to be designed to carry a compressive force of 10 kN and a tensile force of 20 kN. Now, let us discuss about the process of drawing the reaction influence line for statically determinate beams. If the beam has no internal hinges, let us draw reaction influence line for cantilever or simply supported beams. Here is a cantilever beam. The vertical reaction at A due to a unit moving load is 1. the reaction does not change as the unit load moves across the bridge. So, a diagram representing reaction at A, due to a moving load look like this. See figure below. As you can see, the diagram is a straight horizontal line, as if we have taken the beam and pushed it up by 1 unit at point A. This idea of pushing the beam up by 1 unit at support and drawing the shape that results is a convenient way of drawing reaction influence lines qualitatively. Let us see another example. Here is a simply supported beam. Let us draw the influence line for reaction at point B. To do so, push the beam up by 1 unit at point B and draw the displaced shape that results. Here is the influence line. I tells us that reaction at reaches its maximum value when the moving load reaches point B. It is instructive to compare the two influence lines that we have drawn so far. The one for the cantilever beam and the one for the simply supported beam. If both diagrams were drawn by pushing the support point upward, how come one is straight line and other an inclined one? What makes the shape of the influence lines different in these two cases is the support condition at the other end of the beam segment. In case of the cantilever beam, the other end of the segment is free. That is, it is free to move up as we push the left end of the beam up. So the two ends move up together. In the case of the simply supported beam, the left end of the beam is pin connected. It cannot move up or down, but it can rotate, so as we push the right end of the beam up. The left end stays in place, but it rotates, causing the beam to form an inclined line. Drawing reaction influence lines, when the beam has one or more internal hinges. For example, consider this beam. This is a statically determinate beam with a hinge at point B. We want to draw the beam's influence line for reaction at point A. We are going to push point A up by 1 unit, and draw the resulting displaced shape of the beam. The hinge divided the beam into two segments. For drawing the influence line, we treat each segment as a straight bar. So we have bars AB and BD. When we push up, the left end of A goes up, but the right end stays in place. So the influence line looks like, see figure below. But there is a question arises, why does not B moves up with A? Isn't an internal hinge allowed to move up or down, although an internal hinge is free to move up or down? In this case, it is not going to move since the supports at cant4 segment CD remain in place. And since CD is a part of bar BD, the entire bar has to remain in place. That is to say, the roller at the pin at D, prevents the hinge at B from moving up. Now, let us draw the influence line for reaction at C. We need to draw the displaced shape of the beam when point C is pushed up by it. Bar BD is pin connected at D and has a hinge at B. So, if we pushed point cup, the bar is going to displace like this. But only if bar A permits it. A does permit point B to move up, as the bar can rotate counterclockwise to accommodate the displacement imposed by segment BD. Why does AB rotates? Because it is pin connected at A, pins and roller allows rotation. So the influence line for the reaction at C looks like, as shown in the figure. Now, let us draw the influence line for point D. We need to figure out the displaced shape of the beam when point D is pushed up by a unit. First let us figure out how segment BD want to displace, if permitted by the adjacent segment. If we pushed up, given that cannot move, it can only rotate, then BS to move down, like this. But is this configuration possible? Does the adjacent bar permit B to move down? The answer is yes, since A can rotate, bar AB turn clockwise to accommodate the downward movement of B. So, here is the influence line for reaction at D. Let's look at another example. Here we have to draw the influence line for the reaction at A. Push up, while keeping in mind that the bar C is not able to rotate since it is fixed at B. This means cannot move. Therefore bar AC can only assume one displaced shape, as shown in figure. It is important to note that when drawing influence lines for statically determinate beams, we treat the segments as straight bars, unable to bend. That is, it might be tempting to draw the influence line for reaction at A, see figure below, arguing that segment C can bend to accommodate the support conditions. But this is not allowed, since here we are not really drawing the actual displaced shape of the beam. Rather, we are using the qualitative approach to show how the reaction force changes. In statically determinate beams, this change is always linear. What about the influence line for reaction at B? Push point B up at it. What do we get? When we push point B up, C is going to go up as well, unless the adjacent segment limits the movement. But bar AC is free to move up at C, since it can rotate to accommodate the movement. Try to solve the following examples. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.